All right, so this driver is trying to navigate that turn that now there is friction, and we want to know how fast he can go in part B before he starts skidding off the road and ends up in a fiery, horrible crash. And so what I've done is I've drawn the free body diagram of the situation. We're going to keep our coordinate system with x being horizontal and y being vertical because we know we're accelerating in the x direction. That'll be a centripetal acceleration, and we're not accelerating in the y direction. So what I've done here is I've drawn our normal force, and I've broken it down to its y component in red and x component in green, and the frictional force would be contributing to the centripetal acceleration. So it would be inward, parallel to the ramp, giving it an x component in green and a y component in red. Now there's two statements that we need to start out with, and they are that the net force in the y direction is 0, and the net force in the x direction is our centripetal force. Let's expand those two. The net force in the y direction is the upward force of the normal force minus the y component of the frictional force minus gravity. Right? Those red forces, friction in the y direction, gravity, they're downwards, and the normal force in the y direction are upwards, and there's no acceleration in the y direction, so they must add up to 0. In the x direction, we have the normal force and the frictional force both pointing radially inward, so they are our centripetal force. We also know there's one tie-in between the two, and that is friction is fun. It's mu times the normal force. Okay, so all we really need to do is a bunch of algebra at this point. So what we'll do is we will put our y component of normal force in terms of the normal force itself and in terms of theta, which is our ramp angle. And same thing with friction. If we follow that out, we will find this expression for normal force. And we're going to substitute that normal force into the expression for our centripetal force. So if we go back over there, we substitute just like we did before, n sine theta plus f cosine theta. Those are the horizontal components of normal force and friction, and they are our centripetal force. That's why they're equal to mv squared over r. We're going to substitute for friction, mu times n, because friction is fun after all. And then we're going to go ahead and we're going to take that expression we had for the normal force and substitute it in over here. What I've done in this particular step is I factor out the normal force from the expression on the left. Okay. And when we make this substitution, we can see that the m's will cancel out, and then I will multiply both sides by r. And then in order to get the speed, of course, I will just take the square root of all that lovely mess. When you go ahead and you substitute your values in, you will get 21.1 something. 21.1, that's no answer. You get 21.1 meters per second. I hope this was helpful. If, however, you're going too slow, it's going to change your free body diagram to from this to having friction going up the ramp. That would change this expression to your normal force would be up, but so would the y component of your frictional force. So you would actually substitute a plus sign in here. Gravity is still downward, but that would be the only difference for this particular expression. Over here, since friction is now pointing this way up the ramp, the x component of friction would now be pointing outward. And so our centripetal force, our sum of forces, would be n sub x, which is radially inward, minus f sub x, and that would still be equal to mv squared over r. So I hope you found this useful. We'll be back on Thursday. We'll probably go over a couple more of these together in class as part of our review for the unit test on Tuesday.